here, so is what they call the maria, were probably from volcanic. They quite rightly had thought that a huge, massive impact had then brought hot, molten lava up onto to create these smooth, dark surfaces that you see here, this flat, dark mare basins. But you see all these highlands here, which they speculated might have been debris from this huge impact basin thrown up out of here. So that was their general impression of the moon prior to Apollo. So how about a bit of lunar theory? How did the moon form? And at that stage, there was just three ideas. That fission, that in other words, when the molten Earth was rotating very quickly, and a little bit of molten material flung off and formed into the moon. Co-accretion, that's when the Earth accreted material, built up its material from the protoplanetary disk, and just as the Earth was doing it, the moon was doing the same, just to one side. Or capture, that the moon might have been captured, going past in Earth's gravity, been captured. We do a whole talk on the formation of the moon. You probably remember all of those three have some huge problems, but they were just the three they thought of at the time. But Apollo changed that, as you will see. Some of the other age, the age of the moon and how it formed, totally unknown. Its geological history, how it evolved, unknown. And of course, they knew nothing about its internal structure. Okay, so how about the Apollo program itself? What the Command Service Module observations tell us. Let's have a look. So this is the image we saw earlier before. The whole science of doing experiments from an orbit is called remote sensing. And for its time, it was very high precision remote sensing. In that instrument bay, there were no fewer than 10 key instruments. These are them here, each of which we will go through, how they worked and what they told us. But probably the key message is from here, as you'll see, it was a team effort, and they correlated the data from orbit with that of the rocks and so on, and the experiments from the astronauts brought back from the surface, and were able to bring those together to create a picture. So everything was correlated together. And of course, the other thing was the command module pilot was doing was taking a lot of photographs and so on, trying to identify ideal landing sites for future missions. They were doing that the whole time. Sites that were easy to get to, relatively easy to get to, and varying geological interest. Okay, so let's start with these instruments. First of all, there's the panoramic and the mapping cameras, and they speak for themselves, just taking high definition images from above, different features, mapping out the geology and the surface of the moon. They had a laser altimeter, and what that did sent pulses of laser signals down to the surface of the moon. It would bounce back up again, and the instrument would record how long it took, and from there they would work out the different altitudes, and they were able to work out the tomography of the surface of the moon in reasonably good definition to make tomography maps. And from that they were able to identify different regions of volcanic activity, elevated regions of tectonic landforms and so on. And the importance of that was they'd make a note of that, and they could correlate it with the rocks that the astronauts brought back from where they were. And that's how they built a lot of the picture was built up. The rocks on their own could only provide so much information, and the same with tomography. You combine the two and you start to get a better picture. And some interesting stuff that showed, for example, these domes. See these here? And these are volcanic in origin, thought to be from upwells of thick lava coming up, and of course just flowing everywhere. They just formed these rises, these small domes. They're about anywhere between 200 and 500 meters high, so up to half a kilometer. And these are scattered over the moon. So they're a new feature that they didn't know anything about before. And there's these pits here, which is sort of look like craters, but instead of being sort of gentle slopes into them, very steep slopes straight down, and they're thought to be openings down to collapsed lava tubes under the surface where lava would have flowed billions of years ago, and have since all collapsed, and they call them skylights as well, or pits. So they were a new feature that no one knew about beforehand. Then there was rills. This is Hadley Rill. We're having a look at this later on. But the rills are sort of these big valleys that were just channels, rather, that would just meander. And they could go up to about 400 kilometres long. They'd be a kilometre and a half in width. Hadley Rill's a kilometre and a half in width, which puts a whole new dimension. They just look so tiny from orbit. But that's a kilometre and a half wide, about 300 metres deep. But they are thought to be lengths of, once again, where lavas flowed through underground. And of course, as time went on, the lava got moved on and the tubes just collapsed in on themselves. But you just imagine, the size of those things and just the huge amount of lava flowing underneath the surface all that time ago. Okay, then they had these two spectrometers, the gamma ray and the X-ray spectrometers. And the idea here was to help them determine what minerals and elements were on the surface of the moon, but what was their distribution. And I'll show you some slides shortly to look into that a little bit deeper. The gamma ray spectroscopy, light or electromagnetism, comes in a wide range. You've got the visible light here. At this end, you've got low energy radio waves, infrared, and then you've got ultraviolet, higher X-ray, and higher energy gamma rays. So from the surface of the moon, there was gamma rays coming up from two sources. One is the elements thorium, uranium, and potassium are radioactive, and they just spontaneously emitting gamma rays. So they could detect those coming up, and of course each element has its own separate specific wavelength, so they were able to plot those elements where they were. As for the iron, titanium, and oxygen and so on, is that gamma rays, which are high charged, high energy particles coming at high speed from space, from elsewhere in the galaxy, called galactic cosmic rays, they would strike the surface of the moon and excite those elements and excite them to emit a gamma ray. So that was, spectrometer was able to do that and map out the distribution of those elements. Then it had an X-ray spectrometer, whereby X-rays from the sun would strike the surface, excite elements, which would then emit X-rays. So they could also tell the composition of the surface and the distribution of those elements. So they formed maps from there, and I'll show you shortly. They found out that there was regions of those mare, those sort of seas, if you will, those dark patches were very rich in magnesium. The white sort of paler areas in the highlands were very rich in calcium and aluminium. And from then, it helped them reconstruct geological provinces, if you will. Not only sort of landfill provinces, but areas where geological processes were occurring. And these here, these little graphs, okay, so what you've got here, this is the gamma ray spectroscope map. This is the North Pole here. So this is the northern hemisphere of the moon, the southern hemisphere. This is the near side here, and that's the far side, and the same here. And you'll notice the higher concentrations of iron are in the lighter colours, and the darker colours are in lesser amounts. And what do you notice here? Look at this. On the near side, both these, much more iron. You'll find out shortly as the talk goes on why that is so. But that's so clear, isn't it? And it shows the difference in geology between the near side and the far side. Then the radioactive elements, uranium, thorium, and potassium, they mapped out differently. So for this map here, this is the far side, and this here is the near side of the moon. North, south. Look at the difference there. It looks just all at the near side. It's just rich in these radioactive elements. Very little sign of them on the other side. We'll talk about and we'll explain that later on as well. The other thing is here, as we've talked about here, totally different geology. Okay, then there was the two other spectrometers, the alpha particle spectrometer and the mass spectrometer. So the alpha particle spectrometer was designed to pick up alpha particles, which is helium nuclei, 2 neutrons and 2 protons together. And the source of those is that uranium, radioactive element, which we talked about a few minutes ago, that decays, you're probably aware, that decays into lead. But it's not an immediate uranium bang to lead. There's actually a decay chain involved in radon and polonium and so on. And in that decay chain, there's helium nuclei, alpha particles that get emitted as the radioactivity. And they are able to pick that up. And that's a good indicator of outgassing that's going on from the moon. Just gas coming on up as radioactivity produces them. So they're able to look for that, and the mass spectrometer was there designed to have a look. The very atmosphere was very tenuous, but have a look and see what the composition of the atmosphere was. So you can see a lot of science is being done. So they found out that in some locations, you'll find out the moon, a little bit of geological activity. It's compared with Earth, it's dead, but a little bit of geological activity and a little bit of weak outgassing in some locations. Little evidence of an atmosphere, just a bit of helium, neon, hydrogen, and argon. Then there was, interesting, the lunar sounder. That was on Apollo 17, and that was a ground-penetrating radar. It would go down to 2 kilometres deep to probe the subsurface, and the infrared scanner, which would scan the surface temperature and the cooling rates of the surface of the moon. So because of that, they could penetrate 2 kilometres down with the sonar probe. And they found various regions where there was layers of different layers of lava, with obviously different volcanic activity that occurred at different times and different layers and so on. They could detect that. They could detect different regions where they could see there'd been a lot of impacts going on as well. They could detect those. And there was even the regolith, that's the soil, if you will, of the moon. They were able to deduce from that, looking at it, that that was made of just micrometeorites, just over millions and billions of years, just getting hammered with small, tiny impacts that break it all up, the rocks up, to create the soil. The cooling temperature in the equatorial regions of the moon in the middle of the lunar day is about 120 degrees Celsius. There's no atmosphere to speak of, so there's nothing to moderate that. So at night time, midnight, it's about minus 120 degrees. So huge swings in temperature. They found different regions with different, at night time the temperatures cooled very quickly and differed in different regions. The temperatures at the poles, there are some very deep craters where they have PSRs, permanently shaded regions that never see the sun. They sit at about minus 240 degrees. Very cold, that's Celsius. This is some work from the sonar, and they've had all these winkle ridges along here. These would travel for a few kilometres or so, but because they were able to go down into the surface, they could see that these ridges went down, over 1.6 kilometres down, and they were able to deduce from there that these ridges are caused by little faults that have developed in the crust of the moon. As the moon has slowly been cooling down, it's also been contracting, and little fault lines develop and create little ridges and so on. So they were able to deduce that from the radar sonar. Apollo 15 and 16 had a little sub-satellite that they released that went off out on its own doing experiments, and that measured the moon's gravity and magnetic fields, and it showed, we were able to map them out, and it showed little localized crustal magnetic regions, no big global magnetosphere, but there are little regions around the moon with some magnetic activity, mainly based around those lava-filled basins, or mare, those dark regions, because that's where a lot of iron, as you'll see, was in those. Then they had the S-band transponder. Yeah, this is interesting. They used, obviously sent radio signals, and they used the transponder. That was a radio device for communicating, voice communications, but also data communications, transferring data backwards and forwards. And they just use set radio frequencies. As you're probably aware that if something's going to speed up, then it's the signals that go out, the wavelengths gets crunched up a little bit, get shortened, the Doppler effect, and vice versa. If you're going to slow down, the Doppler effect, your little wavelengths get spread out. So they were able to monitor that from Earth, monitor the change in the radio frequencies with their communications and with data and so on. And they could tell if the spacecraft in its orbit, because it should have just been going around constantly, but they could tell it was speeding up at times and slowing down at times. And what is your driver for going around in orbit? Your driver is gravity. So clearly there were regions of the moon below them that were higher gravity that sped the spacecraft up, and they were picking that up from the change in frequency of the radio waves. So they also from there concluded the lunar crust is thicker on the far side. On average, it's about 60 kilometres deep, the crust on the far side, but the near side is only about 40 kilometres deep. Significant difference. Why is that so? You'll find out. These concentrations of gravity, they're called the mascons for mass concentrations, once again, there was difference. They were on the near side, but not the far side, these mascons. Something going on there too. And they related it to probably the increase, that high density lava that had come up and filled these basins. Okay, so that's what the command module saw. How about the surface experiments? What did they tell us? Well, there was 6 main experiments. We'll have a look at those. These are those here. Each one we will go through. Okay, first of all, the seismometer. This is really interesting. So its purpose was to answer the questions: is the moon geologically active? Does it experience spontaneous moonquakes like we have earthquakes on Earth? Does it have moonquakes? But also, what is the internal structure of the moon? Prior to Apollo, they knew nothing, zero, about the structure of the moon. So they set up these seismometers, and they had obviously had 6 of them around the moon. And you'll notice with the moon landings, you'll see a map later on with them, the moon landings were mainly equatorial based, because they're technically a little bit less challenging than landing at the poles of the moon. They also picked different geological areas, but also they wanted reasonably spacing between them so they could set up 6 seismometers at different regions around the moon, try and spread them out as much as they could to get a feeling of any vibrations going on, to work out the internal structure of the moon. Found out the moon is, compared with Earth, it's geologically dead, essentially, but there is some mild activity that is going on they were able to pick up. So 2 causes of a little bit of activity going on. The volcanic activity ceased billions of years ago. We're going to be looking at a timeline later on of that. But those fault movements that we talked about, those little sort of faults from the moon cooling and contracting, create little fault movements. So the crust compresses and breaks, and that creates some steep slopes, those wrinkle ridges we saw, cliffs, landslides. And this here is a rock with Apollo 17, that's Jack Schmitt, next to that big boulder. They worked out that just the position where it was, that came from a landslide that had rolled down from somewhere. The importance of that, you might think, well, that's interesting, good-o. There is importance to that. If you're going to be building outposts, bases on the moon in future decades, you don't want to build one on where there's fault lines and so on, where you could get a rock crash through your base. So that's very important. And the other one is tidal forces from Earth. As the moon in its orbit around Earth, there's tidal forces going on, and they cause very mild moonquakes. And there is a timing difference. Those moonquakes naturally are closer during perigee. When the moon is closest to Earth, they tend to be a little bit more frequent. They caused prolonged vibrations, and they probably behind the landslides as well that are going on. So there is a little bit of activity, not from volcanic heat coming up, but because of the tidal forces from Earth and then the contraction and cooling contraction of the moon. So there is a bit of activity there, and the importance of that is, you don't want landslides. Now, the other one is, to work out the internal structure of the moon, they needed a little bit more data than that, some really good solid vibrations. And this is very typical of the whole, the Apollo program, the whole space program. They never miss an opportunity to do some sort of experiment and not to waste anything. So the ascent stage, you probably remember from our previous videos, and that the lunar module was 2 halves, the descent and the ascent stage, and it would come down and land. And when the astronauts went back up into orbit again, it was just the ascent stage that lifted up, went back to the command module. Apollo 11, they purposely just let it drift out in orbit around the moon. They did that on purpose to see how long it could still function for. And that paid dividends. Think Apollo 13. When the lunar module became its life support, essentially the lifeboat, they knew from Apollo 11 that Apollo 13 would keep them going for a while. So that was that experiment. But Apollo 12 onwards, the ascent stage, when they'd finished with it, they sent it back intentionally to crash into the moon to generate vibrations throughout the moon. They did that with all the missions from the third upper stage of the Saturn V rocket. As soon as they were sort of in trans-lunar injection, given their boost from Earth orbit towards the moon. They no longer needed that, so they sent that on ahead to the moon to purposely crash into the moon to generate vibrations and so on that the instruments that had been there previously could pick up. And they found those generated reverberations like a bell ringing for up to about 55 minutes, which is That's a long time. Why? It's because the moon is it's quite dry. There's not a lot of water and within the soil itself. So it's more dry, and it's dampness in soil that tends to dampen down vibrations, but the moon is drier. So it kept reverberating for about 55 minutes. So much longer and stronger than expected. So, but from there they were able to deduce the internal structure of the moon. That's worth having a look at here. So here's a diagram over here, just comparing it with Earth, and comparing it, and there's a few features that stick out here. So here's Earth on the left and Moon on the right, but you notice the crust, Earth's crust is relatively thin, and the crust on the Moon, the average, is relatively thick. There's the mantle, the bit in the middle, but look at Earth's iron core. That's much bigger than the Moon's iron core. So you're already starting to see, that would explain why the low density, the low mass and density of the Moon compared with the Earth. So the fact that it was differentiated, that's what they call it's differentiated, it's formed into structured layers. And the process that does that's called chemical differentiation. The idea, if you get something that's very molten and mixed and everything's mixed in together, given some time, in particular 100 million years, the heavy iron with some heavy nickel that gets attached, that tends to sink down to the core, the form of any planetary body that's forming. Your lighter elements, like your calcium, your minerals with calcium and aluminium in them, and so on, they are going to slowly float up to the top. And in the middle, you'll get left with your crystallization of your minerals that are in the middle, so like with magnesium and titanium, some iron mixed in there as well. And that whole process is called chemical differentiation. So when you see that, that tells you the implications of that is that the moon was once completely molten before it cooled down to its current state. That's what that information told them. So then they not only got the idea that the structures of the moon, and you can go and look that up at the actual figures going on there. I thought I'd put this in because this is relevant to what we're going to be talking on later on. So the crust up in here, so here's a sort of big, what they call the magma ocean. It was all sort of magma, all hot and liquid. And then it started cooling off and a crust started forming. And the crust is predominantly made of a class of minerals called plagioclase. And they are silicon oxides, silicates, which is silicon and oxygen. Most rocks are silicon and oxygen because they're two of the commonest elements on Earth, so it's no surprise. But they are minerals in particular with aluminium and calcium in them, known as anorthosites. So they floated to the top and formed the crust. In the middle here, you had your silicates, your olivine and pyroxene, in particular silicates. They're very rich in magnesium and iron, also some manganese and titanium. They are heavy and also they're a dark colour. Notice the plagioclase is a very light sort of colour, aluminium and calcium, when I say light, as in pale light. And the mantle formed here. The olivine tend to be in the sort of lower mantle, and the pyroxene tends to be in the upper mantle, but they formed. So then the iron, of course, sink to form the core. But notice this boundary just underneath the crust here called creep. Creep stands for potassium, rare earth elements, and phosphorus. And the importance out of those is that potassium and some of the rare earth elements, particularly the uranium and the thorium, are radioactive, heat generating. And the other thing is they're called incompatible elements. And that when everything else in the mantle was solidifying, crystallizing as they were cooling down, just due to the shape of the crystals and minerals that were forming, the creep elements, because of their size or their shape or their charge, could not fit into any mineral crystal structures that were forming as the moon was solidifying. So for that reason, they were just incompatible. They were slowly squeezed up because the moon would have been, as things were cooling, things tend to rise, and then you get a little bit of further melting and it tends to sink. So it was a real mixed hot pot of stuff for a while that was going on. And these creeps, elements, slowly worked their way up and formed a boundary layer between, just right underneath the crust, between the crust and the mantle. Eventually, those minerals with creeps in them did solidify, became rock, but this is very relevant, they were the last minerals and elements to finally crystallize into a solid form. That's important. So that's, in other words, the very last stage of that whole chemical differentiation and solidification process. The last 1% to solidify, there you go. Now, and I call it, that's the primary crust, because we'll talk about primary and secondary crust. So that would have been the primary crust that formed when the moon first cooled down. But then you had hot bits of mantle that was coming up and down and so on. The creep was still, generates heat, and the crust got mixed up a little bit with things, got stirred up, and it developed a secondary crust. Okay, then there was the magnetometer. So that was an instrument they set up to measure magnetic fields. And as I mentioned earlier on, from the command module instruments, they found that the moon does not have a global magnetosphere like we have on Earth, but it does have little localized regions of magnetic fields. And they varied between regions of the moon, and it makes sense that there's different mineral concentrations will give you different degrees of magnetic fields, but also the timing, different times, different regions of the moon get different magnetic field strengths. Because as the moon's going around the Earth, magnetic field, and as it's going around the sun as well, you've got a magnetic field there, and there's interactions and play going on there as well. That was interesting. Then the heat flow detector. So they buried these down 2.3 meters into the soil, trying to detect if there was any heat flow coming up from any volcanic geological activity underneath. And the answer is really very, very little. So there's no real volcanic activity, geological activity going on underneath. The geological activity is mainly because of the shrinking and cooling of the moon and the tidal forces, and a bit of hardware landing on it from time to time. So this is the laser ranger, the instruments that they set up on the surface of the moon. That's still in use today by the scientists. And the idea of scientists on the Earth send a laser signal up to the moon. It hits the reflector there and comes back, and they measure the time, and they can very precisely measure the distance between the Earth and the moon, very, very precisely. And they predicted that if the laws of mechanics and physics are correct, the moon should be receding from us so steady state of about 3.8 centimetres per year. And indeed, that's what they found, and that is still so. You might say, really, why is the Earth and the moon separated by 3.8 centimetres per year? And that's to do with the tidal bulges. The two interact gravitationally. So the moon does a little bit of a bulge here with its solid surface, but not much. But of course, we've got oceans on Earth, so we get these big tidal bulges here that we call tides, that we call ocean tides. And of course, the Earth is spinning, so the tides are going in. The Earth's ocean bulge is always just ahead of the moon. And so that tends to pull the moon forward. And it's a little bit of orbital mechanics that you're in orbit around something, and if something pushes you out a little bit, you're going to go into an outer orbit as you get pushed along out. To the point of a bit of orbital mechanics. If you're in a spacecraft and your mate ahead and he's in his spacecraft, and he says, "Hey, catch up with me, have a look at my new spacecraft, my new fancy one. Oh yeah, that looks good." If you accelerate, what will happen is you'll go forward, but as you're curving around, you'll actually end up going to a higher orbit. And of course, what drives orbits? Gravity. The further you get away from something, less gravity, less driver. So your orbit slows down. So you'll actually slow down away from him. So the idea, if you want to go and catch your buddy, is to slow down, drop into a lower but faster orbit, go ahead of him, and then come up beside him. And then admire his new spacecraft. And say, where might you be heading with that new spacecraft? So that's what's going on there. That's why the moon is slowly receding. And in the process, the Earth's rotational speed is gently slowing down. Then there's they had a little instrument measuring the atmospheric composition on the surface of the moon. And once again, they confirmed, look, it's very tenuous. This subtle atmosphere, but nothing to speak of. Then this is sort of a picture you often see. 6 of the missions set up a solar wind experiment, and they had an aluminium foil, essentially what it was, and they'd set it open like that, and as particles came from the sun in what they call the solar wind, they get embedded in the aluminium foil, and at the end of the mission, the astronauts wrap it all up and retrieve it and take it back home again. And because, of course, this was the first opportunity, they were aware of the solar wind, but this is the first time they could set up a nice steady experiment outside of Earth's atmosphere and its magnetosphere. So it was really the first opportunity they could do that. And it showed that 95% of the solar wind is protons and electrons in equal numbers. and about 5% of helium nuclei, also known as as alpha particles, and calcium through to iron, just trace amounts of those. Okay, so that's the surface experiments. So what do the rocks tell us? They brought back 382 kilograms. So they told us a lot of information about the moon, how the moon formed, how it's evolved, the history of the moon, but also they told us some stuff about the history of the solar system as well. Let's find out. I've split this into two. First of all, where did the astronauts go to get the samples? And that's very relevant and very insightful. And why did they choose those sites? And then we're going to have a look at the individual rocks, what they showed, and then we're going to bring it together to form our picture. So let's look at the astronaut landing site. So there they are there. You've probably seen that a few times. So look, here's Apollo 11, just at the Sea of Tranquility, just sitting right there. And there was a few reasons why they wanted to land there. It's nice and flat and smooth. It was the first landing. You're going to have some landings on some of those Mare to bring some of those rocks back. So let's make it the first one. It's smooth, technically a bit less demand than the others. You might think, gosh, that's pretty close to the highlands and stuff. That's not really out in the plains. From Sabine Sea crater through to Tranquility Base here, that's 85 kilometres. So it actually is a reasonable distance. But it was clear of the ruggeds, and it gave them an opportunity to look at these mare, or these seas, if you will, and bring some rocks back of there to look at the geology. Apollo 12 went to the Ocean of Storms, and once again, that was a very flat sort of mare region here. You can see here, once again, no mountains and hills in the background. They visited a crater named Surveyor Crater, because of Surveyor 3 spacecraft from 2 years earlier there was landed beside that crater. And they thought, let's go and land by there. A, to prove we can now do a pinpoint landing. 2, let's go and grab some bits off the Surveyor 3 craft and bring back to Earth and see how they fared in the 2 years in space. But really of importance, they were there, particular Surveyor Crater. And remember, we talked about why do they go and visit craters? Because if you go to a new region to do some geology experiments, what's the first thing you want to do? You want to start digging and drilling. You want to see what's down below it and so on in the different layers. And of course, with craters, nature's already done it for you. And so it tends to haul all the material out and spread it out very neatly for you, whereby the stuff furthest away from the crater is usually the stuff that was on top. And the further you get to the rim of the crater, you're getting more to the deeper and deeper material that was excavated out. But these guys were one step ahead again than that, because they realised some of these areas that were these nice big excavating craters, but the material, the background of that region where that crater was material that had been deposited there from a larger crater, more deeper, more earlier, more interesting crater further down the line. So that was just ingenious thinking. In Surveyor Crater, all this material here was thought to be from here it is, Copernicus Crater up here. So Copernicus Crater is a decent size. That's it. There's a nice close-up of it there. So when the impact that hit Copernicus Crater, all its ejecta was spread right through here. And they thought that particular region, the geologists were pretty convinced that was all from Copernicus. So here's all your debris from Copernicus, an old large crater. And of course, then you excavate amongst that. How clever is that? So that's why they landed there. Then Apollo 14, same principle. They landed in the Frau Mora Highlands up in here. And they went and visited Cone Crater, this one here. And that, because all this Frau Mora region here, formation, they thought is material from this huge, massive old impact basin called the Imbrium Basin. So this was about 3.9 billion years old, this basin that they found it later from the rocks. But this basin was formed from a huge, probably a protoplanet in the early days of the solar system, about 3.9 billion years ago, that struck here, created this huge big basin and spread all its debris here along this formation. So that's why they were there. And once again, nature had done the drilling for them again. So that was very important. They figure that there was a period in the solar system, early days, called the late heavy bombardment. And that's when this big area, just like you've got the asteroid belt in the inner solar, between the inner and outer solar system now, there was another belt of small bodies in the outer solar system, inside with what we call the Kuiper belt. And early days, the large outer planets did a bit of migration and moved around. And Neptune and Uranus did a complete turnaround, but they ploughed outwards and they scattered a lot of that material into the inner solar system that gave all the craters and so on. It's called the late heavy bombardment. And they were keen to know when did that occur. And they suspected that this Imbrium basin was formed because of that. Let's just go back. Was formed because of that. So if you could date the rocks, which are all spilled out here, let's just get this under control, shall we? Here it is. No. Yeah, we're in business. There it is there. So all this material from here, the Imbrium basin going down here to the Framora formation, will tell us when that late heavy bombardment occurred, about 3.9 billion years ago. Well, actually, it was over a period of time in the end. They decided it was probably from about 4.8 through to about 4.1 billion years ago through to 3.8 billion years. So let's move on again. Apollo 15, they landed here, and it was right on the foot of the Apennine Mountains. So here's huge big mountains here. This is an elevated but flat area here of Mare, and here's that big Hadley Rule that we saw earlier on. So the idea of landing here was a nice elevated but flat zone, and it was a nice transition period between the flat Mare and the highlands. So that's why they landed here. And here was Hadley Rule. So that's 300 metres deep and about 1.5 kilometres wide. Apollo 16 landed up here in the Descartes Highland regions, so the oldest areas of the moon. That was thought to be Plum Crater. They were very interested in here. A lot of craters up here, and they thought they were probably volcanic in nature. So they went to Plum Crater and picked up a lot of the rocks, the debris from here, and they knew that would tell them, we'll talk about that later on, whether it was volcanic or impact. Then Apollo 17 landed in the Taurus Littrow Valley, and that's in here. As you can see, it's a huge big valley, sort of flanked by 2-kilometre high mountains. So once again, a nice elevated region there in the highlands, and once again, a lot of mixed geology between highlands, ancient highlands, and young volcanic features going on here as well. So and here are the 6 sites here. You can see that they're reasonably equatorial. They weren't near polar latitudes. They're reasonably well spaced apart for seismology purposes and also geological purposes as well. Nice sampling of different geological regions of the moon. So that's where they landed and why they chose those landing sites. So what did the astronauts bring back for analysis? Let's have a look. First of all, there's 3 basic types of moon rocks: basalt, anthracite, and breccia, which we'll talk about. So first of all, the basalt rock. And this is a sample here from Apollo 15. It's 3.5 billion years old. What do you first notice about it? It's quite dark, isn't it? Quite black looking. And that's because it's a lot of iron and magnesium in it. And that was volcanic rock that's come up from underneath, flow that would have spilled out over the surface as lava and then solidified, formed those large plains. The second thing you notice about it is, look, it's full of cavities, isn't it, from gas bubbles. And that's because of when volcanoes get erupted. There's a lot of gas coming up too, a lot of outgassing. Volcanoes spew out a lot of gas, carbon dioxide in particular, as they're erupting. So that causes all the bubbles in there. So that's another clue that you're dealing with volcanic rock. And it had high concentrations here of the pyroxene, which we spoke about. That's the silicate mineral rich in iron and magnesium, giving its dark colour. It also had some ilmenite in it as well, which is a titanium iron oxide mineral. It's quite dark as well. But there was also some of that plagioclase, the silical minerals rich in calcium and aluminium, the paler stuff. You think, how did they get in there? Isn't this from the mantle? Yeah, but lava would have flowed through the highlands and the crust and stuff and picked up a lot of that stuff along the way and mixed things through to form that, what they call the secondary crust. And there they are there. That's just the big... So this here is where mainly the basalt is that's come up and formed these lava that's come up and formed these flat sort of seas, or mare as they call them. This is a sample of an anthracite rock from the crust, and you can see here your first impression, yeah, it's very whitish, pale in colour, isn't it? Very light, and it's very low density rocks, hence they floated to form the crust, and it's mostly of calcium rich and anthracite, the plagioclase. It's the dominant rock in the highlands, and it contributes to its very bright appearance too, because it's reflecting more light. And then the third type is the breccia. And breccia rock is composed of all different sorts of rock types that have all just been smashed together through impacts and under intense pressure and temperatures, has been cemented together to just form a hot potch of just multiple layers of crushed up rock of different types. And you see those, this is from Apollo 16, around Plum Crater. And of course that told the geologists that Plum Crater and all those craters in those Descartes highland regions were all impact, not volcanic as they thought they would be. Apollo 15 and 17 found a whole stack of glass beads, green. Apollo 15 they were green and orange on Apollo 17. They found these glass beads, which they were quite excited about. And I don't know if I remember it very well when Apollo 17, it was in the news, and I've seen clips since. Jack Schmidt yells out to Gene Cernan, "Wow, hey, there's some orange soil over here." And Gene yells back, "Don't move, stay exactly where you are. I'm coming over." So that really got excited, some orange soil, and that was these orange glass beads in there. And that was important because the glass beads, they estimated they were between 3.7 to 3.3 billion years ago, and they would have been formed by molten hot material shooting material up into the air very, very quickly, and that creates the glass, the spherical glass beads, and then they cool down very quickly as well, so they got shot up in the air to create the glass. That's how they make glass. And so these hot instead of just lava going up and just spilling out, like filling up a basin or those little domes that we saw earlier on, there were parts of the moon where there was stuff flying up high, such as here, the cool fire fountain explosive episodes, because it's those sort of explosions, intense heat firing up into the air, then rapid cooling as they come down, that form glass beads. And they were able to date those as well, so they knew where on the moon and when on the moon there was explosive volcanic activities. So let's have a look at some of the geological findings as a rule. First up, all the lunar rocks were extremely old compared with Earth's. The Highland crust samples were about 4.4 billion years old, and that told them that the moon probably formed about 4.5 billion years ago. Why? It takes about 100 million years to go under chemical differentiation, and then for that crust to form, about 100 million years. It would have been molten for then. The rocks were 4.1, so that puts it formed at about 4.5. We know the Earth very roughly, and I've got the timeline later on with exact figures, but just very crudely, top of your head, you tend to say the Earth is about 4.6 billion years old. They know that from meteorites, radioactive dating of meteorites. So we know the Earth's about, when the solar system formed, about 4.6 billion years ago. The lunar rocks were 4.4. That told them the moon formed about 4.5 billion years ago, when the Earth was about 100 million years old. So that was an important clue. The Mare samples, with the black stuff, those flat surfaces here, they were mostly about between 3.5 and 3 billion years old. And what that tells you the timing very roughly of when you had these big impacts and then you started getting volcanic activity spilling up. We've got some diagrams of that later on. All the rocks are igneous rock. In other words, rock that's formed from solidifying hot liquid lava, as opposed to, say, sedimentary rock, for example, like sandstone and limestone that's just slowly formed. And, of course, the breccia, but there was no sedimentary rock. So that, from there, that tells you one thing, that the outer proportion of the moon was once completely molten. So we already know from those rock samples there that the moon formed about 4.5 billion years ago, when the Earth was about 100 million years old. We can also have got evidence now that says the moon itself was completely molten at one stage. Okay, so Apollo 11 and 12, remember they were in the Mare, the flat area. Their basalt rocks differed in age and composition. The Sea of Tranquility, Apollo 11, the rocks were about 3.8 billion years old, mainly pyroxene in the plagioclase. Apollo 12 at the Ocean of Storms, they were younger rocks, 3.3 to 3.1 billion years, mainly olivine and a little bit less titanium. So that had implications. Difference in age and chemical composition of those Mare infers that the volcanism activity that caused the Mare was not one single moon-wide event. they occurred at different times in different parts of the moon. So that once again, this is the information they were getting. Starting to form a picture. The other thing from Apollo 12 and 14 rocks, they were about 4.0 to 3.8 billion years old, and they were rich in that creep, that potassium, radioactive potassium, the urium, thorium, the rest of the rare earth elements and the phosphorus. They were rich in that. And remember that Apollo 12 and 14, where did they get from? Remember that was from Survey and Cone crater respectively, which was ejecta from the Copernicus and crater in the Imbrium Basin retrospectively. So the fact that there was that creep material, remember that creep was that incompatible elements, heat-generating incompatible elements that were just squeezed up to form that little boundary underneath the crust, and they were the last to solidify. So that tells you that if you see the creep, that told you that they were the last stages of crystallization and solidification of the moon, and of course it gives you the date. So that implies that the late stage differentiation and the late heavy bombardment stage were about 4.1 to 3.8 billion years ago. So that's how they worked that out, because they were very high in creep. And that was the advantage of going to those deep, see where the deep craters were that would have been formed from the late heavy bombardment, see where all that ejecta was, and go and visit a crater and amongst that ejecta. So from there, the implications were that the chemical differentiation, the solidification, was complete by 4 billion years too. Another little clue they're digging up. So just all these from these rock samples and stuff, what the picture they're building up of the history of the moon. So Apollo 15, as we mentioned, visited the Hadley Rill, which was there, and that's about 3.3 billion years old, those rocks. So that tells you the implications of that, with that there was ongoing activity with lava, because they were formed from lava tubes. There would have been underground lava quite happily flowing about 3.3 billion years ago. And that's consistent with the glass beads. Remember, Apollo 15 and 17 found the glass beads that showed intensive explosive volcanic activity going on at the time. So it's all starting to tie in and form a picture. Apollo 16, who visited Plum Crater, as I mentioned, that was all ejecta rock, which told you all those craters were impact. There was no signs of any rocks indicating any volcanic activity up in those highlands. It was all called pristine anorthosites in the region, meaning it was all primary crust, which is beautiful. So it wasn't secondary crust that had been all mixed in with a bit of lava and some volcanic material going on. It was the original primary crust when the moon first cooled down. So they were invaluable samples to get their hands on to analyse, look what minerals are there, and particularly date them. And the ancient rocks are up to 4.46 billion years old. That would have told them when the moon first solidified. And there you go, the implications. The lunar craters are almost all impact craters. The primary lunar crust, is because they were able to analyse that, is those plagioclase rich and formed by the flotation of the lighter elements on that magma ocean. And it also told them the crust formed early as well. The lunar material is very low in volatiles. That's elements that tend to evaporate very quickly. That's very volatile, and under heat they evaporate. And such as water, potassium, and sodium. So that told you that when the moon formed, however it formed, it experienced intense heat that essentially vaporized those the water and sodium and potassium, because there was less of them in there. Oxygen and titanium isotope ratios. So the isotopes refer to, we get an element, same amount of protons in it, but different amount of neutrons, and they're called isotopes. And you get ratios of oxygen and titanium, ratios of the different isotopes. The oxygen isotopes differ depending how far out in the solar system you are, what orbit. So the moon's oxygen isotope ratios was exactly the same as Earth. So that implied there was a common source between Earth and the moon somehow. They're linked in together, but also all within the same orbital period from the sun. And the titanium isotope ratios, that is really fine-tuning the stuff. Very rarely do you get two objects in the solar system with identical titanium isotope ratios. So that was a real clue that the formation of the moon was very much tied up somehow with what's going on Earth. So both those observations and the dating of the rocks support, which we're going to talk about shortly, the giant impact hypothesis of the moon formation about 4.5 billion years ago, when the Earth was about 100 million years old. So remember the pre-Apollo? I mentioned those three ways the moon could have formed. No one would have thought of this back then, but suddenly this became apparent. Oh my gosh, this just explains everything. And explains why our moon is so unique. It's so different to any other moon in the solar system. The other thing I wanted to introduce here is the concept of crater dating. So from the command module pilot, when it was imaging, they were able to look at the surface, but make a note of the distribution of craters in terms of numbers of craters and the sizes of craters. And then they were able to correlate those findings with the dating of the rocks that the astronauts brought back. So they knew, therefore, they got used to that if you get certain size craters and certain numbers, that implied, if you draw them in graphs and stuff, that surface is X amount of millions or billions of years old. So they used that to date the surfaces on other planets. For example, Mars. They're able to look at a region on Mars, look at the numbers of craters and the sizes of craters, and they know from the correlation with the lunar experiments, they can tell you the age of the surface on, say, Mars. So it's very important, and of course that, as you've talked about, it gave them a lot of good history on the solar system's history, such as that late heavy bombardment. Okay, so that's what the rock tells us. Let's conclude now and pull it all together to form a big picture. I thought I'd do put it into three. How the moon formed and evolved, what we've learnt so far. Let's do all that. We've talked about the craters and the dark Mare and the pale highlands, but we'll bring that a little bit together to and make more sense of that. And then, as we talked about, there's this dichotomy between the far side and the near side, not only in the crust thickness, but as you saw in the distribution of elements and so on. So there's completely different geology, as you'll see. We're going to talk about that too and explain it all. So you're really going to know the moon really well when you leave here tonight. Well, I hope so. So let's talk about the giant impact hypothesis. And this first came out after the Apollo moon landings, and it was thought that when the solar system was early on, that the Earth was about 100 million years old. It was still molten. It had undergone chemical differentiation, so it had a bit of sort of some crustal material. The lighter material on the crust, it had a medium mantle, and the iron had already sunk down with the nickel to form the core, but it was still molten. At that time, another protoplanet about the size of Mars that scientists have just called Theia, that came along and they collided. That was no sort of coincidence either. It was a pretty violent, the early solar system was a pretty violent place as things were forming. Things were colliding all over the place. Really? Yeah. Look at Uranus, that's completely tilted on its side. Venus, goes back the other way and so on. So those are all from impacts in the early days of the solar system. So Earth was no exception. It copped a protoplanet about the size of Mars called Theia. It hit Earth at a oblique angle, and that gave the Earth its axial tilt. And the theory was a little bit of debris flew off, probably a mixture of the both of them, and then coalesced around outside and cooled down and formed the moon. There were some problems with that, is that it couldn't explain how quickly the moon and the Earth are all going round and spinning so quickly called the angular momentum. Couldn't quite explain the complete composition of the moon. The moon would have formed, according to those models, reasonably close within what they call the hills region, whereby that if you're too close to a bigger body, another body of mass, the gravitational forces will just rip you apart. So there was all these sort of things going on as well. So, but that was the most likely explanation. And then in 2022, some new computer models confirmed that this is indeed correct. They just made some high-resolution computer models and refined it all. And they found that the debris flung in that Theia, as it hit Earth, instead of mixed material going up, all of Theia would have been completely incorporated into Earth, and it was mainly the material from the Earth's sort of crustal outer regions, a little bit of its mantle, that then got flung out into orbit. And that explains, by the composition of the moon, that titanium and oxygen isotope ratio is identical. That explains that beautifully. It also explains why we got a thin crust, because it was a lot of that cooler as Earth was starting to cool. A lot of that lighter material had already formed. So a lot of that material that went up, the lion's share of it, was actually from Earth's about to become crust. Earth's iron had already gone down to form its core. So that would explain the low density and the thick crust that eventually formed on the moon. It would also explain why the moon it's got a small core compared with Earth's. And it would also explain why Earth's actually got a decent sized core, iron core, because it incorporated the Thea's one as well. So all this is explaining. But it also showed that two objects came out. One then they went round, and one slowly got reabsorbed, went back into the proto-Earth, and that pushed the other one out beyond the Hill and the Roche limit, which means that the other moon could slowly form on its own without getting ripped apart. So that it all explains it all. And I've got a few slides here. I've got a little video that goes through with this here. We'll see how sound goes. How's sound go? We'll see how it goes. Yeah, it's only electronic music anyway. It's nothing of, yeah. So, okay, so here's the little video. And otherwise I'll just put my voice on, but, oh, there we go. We might need the volume down. I think you've got volume. So here it is, here's the clip. No, do it twice here. So this model fixes all the problems that it previously had. So there's the one going back into the Earth. And this one forming the moon is at a reasonable distance where it's nice and stable. It's all molten, so it becomes round and then it solidifies. That's our best model, and that's matches up with all the geological findings in that computer simulation.
Did the moon have to split into two parts to make that proper map?
Yes, Tony, two blobs, absolute two blobs. So as with the conservation of angular momentum, as one got absorbed, that pushed the other one out, in for that Roche limit, and made it into stable. Because the theory was, the first computer models from the 70s just showed that one blob was formed. And they thought, it's too close, it's within the Roche limit, it's going to get torn apart, it doesn't fit, something's wrong with the model. But this model, it's a high resolution one from 2022, extremely, I think it was 1,000 times better resolution than the previous models. And yet it showed that two blobs formed, and it makes sense that one falls back to Earth and that pushes the other one out into orbit. Yeah, absolutely right. I've put this timeline together here. That's in your handout, or if you're watching online, you can just pause it for a while. Need to go through every detail here. But you can see the molten Earth formed, and here I've been more pedantic and put more accurate pictures, or dates here rather. So the molten Earth formed here, about the official figures, about 4.567. No one would argue if you just said off the top of your head 4.6 billion years, that's fine. 100 million years later, that's when the molten moon would have formed. And then the chemical differentiation, the solid crust would have formed, and then the final solidification of the mantle. Then along came the heavy bombardment, the late heavy bombardment, form of the basins in the mare, and that's between about 4.1 and 3.8. And then large-scale volcanic activity, in particular with the beads getting formed and so on. So if you're looking at sort of 2.8 to 2.9 billion years ago, pretty much mainly activity had ceased, and a little bit of small volcanic activity had ceased about 120 million years ago. So that sort of just gives you a nice timeline of how the moon formed and evolved. That's all from that geology. Here's the glass beads that I mentioned here from the explosive volcanic activity and over this sort of time frame here. Okay, so let's just look a little bit further about these lunar craters and mare. And you might think, well, craters, we now know that they're pretty much all essentially formed from impacts. Small number of tiny small ones are thought perhaps related to volcanic, but for argument's sake, you can say, look, they're all formed from impacts. And you might say, well, wasn't that damn obvious? Do they have to go to the moon to find that out? Yeah, it was interesting. It was only after the First World War that they realised that craters could form from impacts that were around. They thought, well, impacts come in at oblique angles, so all the craters should be oval, but look at all the craters on the moon, they're round. It must be volcanic, calderas and so on. And it was only at the end of the First World War where they went into no man's land and looked at all the craters, where the projectiles had all come in, of course, at angles, but all the craters in no man's land were round. And it's because, of course, the huge amounts of energy involved when something at high velocity, because the energy is, I might have have I got the little formula up here somewhere? No, I haven't. No. Yeah. Here it is, yeah. The energy involved is half mv squared. So the velocity, you're talking huge velocities. You square that, that gives you a massive number for the amount of energy. And it's, you know, a relatively small object, a rock will hit, but it's the energy that gets expelled from there with the sudden abrupt stopping of it. All that kinetic energy gets released, and it's that kinetic energy that's spreading out in all directions that causes the crater. And as you can see here, so the crater's round because of the large velocity, and it's the explosion of the release of that energy that causes the crater, not an indentation from the rock itself. So yeah, they are pretty much, for all intensive purposes, they're impact related. Tiniest amount of small ones, you know, like your domes and your cones and stuff in the end of reels. But if you see a crater on the moon, you say it's impact. So now, how about these lunar mare and stuff? So we've talked about probably from large impacts that form these and volcanic activities in the highlands. So how did that all come about? Well, usually with this late heavy bombardment stage, when the asteroids or comets, if you will, would have been very large at the time, there would have, here's your lunar crust, your hot molten magma below. You would have had a collision that created a big crater like this, with a huge debris piled up. This is just me with PowerPoint here, just messing around. I was watching a TV program of sorts, but so just crudely doing it. And you got the big mounds either side here, heaped up ejecta. But because of all the forces and the depth of it through the crust, cracks and little fissures develop down here into the hot molten. The hot molten starts rising, filling up the crater or the basin to form a flat surface, which then cools down into the dark mare or seas like that. And of course, this area here, because you're talking huge amounts here, forms your highlands, all this area around here. These are where all your highlands and your mountains are, and they're created from this massive big impact here, all the energy released. All the highlands were created from the debris, and then it would have had little cracks and fissures, which hot molten came up here, hot molten magma, and then solidified, and it's dark. And so that's why you get that. And there you go here. I put this picture back in because it's nice. It just shows those big highlands. And those highlands are essentially crustal material from down here that's been biffed out and thrown around here. And as it showed, Apollo 16 up in the Descartes highlands showed beautiful, pristine, primary crust, perfect stuff for them to analyse. So that's why the moon looks like it is. So how about why this dichotomy? So look at the near side of the moon. Notice the difference just to the naked eye. Look, there's all these dark mare here, and you see one there, small one, but they're not on the side. It's just heavily cratered. That tells you the age of the surface too. So what's all that about? And it's about because of two things. Asymmetric heating due to tidal forces with, we're going to look into each of these in a minute, tidal forces with Earth and a very large lunar impact. So the moon was molten or so, for 100 or up to 200 million years it would have been molten. And because after about 100 million years, it gets tidally locked. I think if I got a slide here for that. Yeah, it becomes tidally locked. Tidally locked here means that here's locked here. See, one side of the moon rotates at the same rate at which it orbits. So the same side is always facing us. And that's just a law of physics that happens just because of tidal forces that create friction. And that's the most stable thing is when the two marry themselves up and become stable like that. That's the most natural thing that happens with time. But of course, in the meantime, while all that's going on, the moon's interior, because of those tidal forces, creating that friction until it gets totally locked, there's a lot of friction and heat being generated within the moon. So that means that the moon's interior, a lot of heat's generated, and of course it's going to be most maximum closest to the Earth, where the tidal forces are much stronger. So the internal heat would have been higher, but also, remember at that same time, Earth was molten and would have been radiating heat, and you would have had one side predominantly facing the hot Earth, so that's a lot of heat's going to be imparted to the moon there. Meanwhile, the other side would have been constantly facing the cold sun, the cold of space rather. So you can see one side was getting hot and the other side was getting cool. And when things cool, they start solidifying down, and that's why, for starters, you've got your thicker crust. The average side, the depth of the crust on the far side is 60 kilometres compared with only 40 kilometres on the near side. And that's why. So within the first 100 years, the moon became totally locked, so the far side cooled and solidified a lot faster because less internal friction because of the tidal forces and constantly facing the cold of space versus the heat of the molten Earth. And indeed, the Chang'e 6 mission middle of last year came back, got some samples from the far side and brought them back, and they found once again they were basalt rocks, primary plagioclase, which then orthosite, so that tells you that's pristine primary crust that hasn't been altered by a lot of volcanic activity. Very little olivine from the mantle. It was predominantly these anorthosites, this primary pristine lunar crust. And interesting enough, that sample they brought back was significantly lower in those creep, the radioactive creep elements that produce heat, which told us that the near side and the far side they got different impact in volcanic histories that created that thicker crust. You might think, why is there less creep in there? Let's have a look. So the idea is the far side minerals began to crystal and solidify up first. Less internal heat and also cooling off to the cool space a lot quicker. So the radioactive elements, your thorium, uranium and your potassium, lingered in the melt, and they tend to move to the hotter near side, adding heat, sort of a positive reinforcement, just sort of adding more heat, so to speak. And that created on the near side much more volcanic activity and lava flows with the lava plains that you just didn't get on the far side. So all the radioactive, not only was the cool side, the far side cooling down so it solidified quicker and was more solid, but also the creep material was all moving to the near side because of that. And that would tie in with the Chang'e 6 samples. Okay, thinner near side crust. Also, that would explain why you've got the layer underneath the crust, which remember it was Apollo 12 and 14, had a lot of creep in there because of the cool more creep had built up on the near side. And it also explains why you got the numerous maria, because following those huge big impact basins that formed from the late heavy bombardment, the crust was a lot thinner on the near side. So little cracks and fissures happened. It was hotter underneath as well. So the lava flowed up and filled those basins. Far side, the crust is 50% thicker. So of course, a lot of those those big basins that formed didn't form crack and fissures. There wasn't a lot of hot lava underneath them anyway, and so the mare didn't form. Now there's another reason again, is probably the moon experienced in those early stages a very large impact. And down at the South Pole, in particular, there's the South Pole Aitken basin, which is the moon's largest and oldest basin, about 4.25 billion years old, and it was formed by a massive impact. And this is it here. So here is your South Pole. This is all far side of the moon, and here's the Aitken crater here, just to orientate yourself. This huge area here is a massive basin, and some sort of protoplanet or large asteroid must have come in and struck the moon at an oblique angles and then created that massive basin. And that heat plume, once again with their computer simulations, a large heat plume would have carried all that creep material that was near the surface. Remember, it was the last of the solidification, so it's tended to be just underneath the crust. That would have created a heat flow, which would have pushed even more creep material over to the near side. Once again, reinforcing that whole thing, just making that crust thinner and making the molten magma underneath a lot hotter, getting more volcanic activity. And so that explains it. That explains why the other side. So I put this up, this beautiful picture of the Apollo 15 command and service module, just reminding us that exploring the moon was a team effort involving the astronauts on the moon, setting up the surface experiments, bringing back the rocks, all the instruments in that instrument bay packed in there with the command module pilot, and of course all the scientists on Earth. It was very much a team effort. And there's one message you take away from tonight, it's this: the Apollo space program, it just, as I've illustrated to you, I hope you've seen it, it's just transformed our understanding of the moon. And I hope you've enjoyed exploring the moon. Thank you very much. I just put that up for fun, a lot of you haven't seen that. So any questions? Yes?
First question is, I remember the picture of the magnetic field generated by Earth is so big.
Yes.
So I wonder if the moon is covered by the magnetic field of the Earth at all.
Yeah, so the question is, Earth's got its global magnetic sphere, magnetic field lines, and is the moon under the protection of that? No, I couldn't tell you the exact distance of how it extends out, but the moon's 385,000 kilometres, and it really gets very little of any protection from that. The moon is on its own in terms of getting bombarded with solar wind. Yeah, but good question, yeah. I couldn't tell you exact figures, but it's the moon is well outside the parameter of the global magnetosphere. Well outside it, yeah. But good question, yeah. Any other questions? Otherwise, we're all done. Now, next month, I was going to do it this month, but then I had suddenly did this talk. I wrote this talk because a few people had asked for it. But the Vera Rubin Observatory, that's new, that's just sort of seeing first light and produced all its first images and stuff. That's promising to blow astronomy out of the water and stuff. So that's what we're going to be talking about next month. Is there a question online?
No. It'll be nice to talk about the observatory. Yeah.
So it's the Vera Rubin Observatory is what we're talking about next month. Otherwise, we're all good. Drive home safely. Thank you very much. Okay. We're all finished. Lights.